Good morning, welcome to
Family Math number 108.
Family Math number 108. So yesterday we made this neat pattern about powers of 3, right?
Yeah.
Yeah, and that idea came to us from this fun pattern website that this guy, Frederico, sent to us. Do you know he's an Ultimate player too? Isn't that cool?
Yeah.
Math teacher and Ultimate Frisbee player?
Cool.
Does it get better than that?
I don't know. I'm not sure.
Probably not. And we watched these prime number patterns go on forever, and you asked me a really interesting question. What was it?
How many prime numbers are there?
How many prime numbers are there? Do you know the answer?
I think there's infinitely many.
Do you know the answer?
Yeah, there's infinite because numbers go on forever.
Ah, interesting. Okay, so numbers do go on forever, because like any integer I write down, what can I do to always just get to the next number?
You can add 1.
Right, I just go x plus 1. So that means numbers go on forever, but that doesn't necessarily mean that prime numbers go on forever. So I want to show you 2 really neat facts about prime numbers. Okay, the first is that there are infinitely many. And you know who proved this, or who the proof is attributed to?
Who?
Euclid. Where do you usually hear Euclid's name? What branch of math?
Geometry.
Geometry. Yeah, but he did some other stuff that wasn't geometry too. So here's Euclid's proof. So assume first there are only, finitely many primes. Okay, let's call them prime 1, prime 2, prime 3. We go up to prime n. Okay, and that's it. That's all there are. We've written down all the primes. Okay? Now I'm going to show a contradiction. All right?
Yep.
But first let me show you a couple examples. Let's say it was only 2 and 3 were the only primes. That was it. Okay? We could multiply 2 times 3 together and add 1. 2 times 3 plus 1, which is 7. Now, how do I know that 7, or 2 times 3 plus 1 is not divisible by 2?
Well, you did 2 times 3 plus 1.
Or it's an even number plus an odd number, which is an odd number.
Okay, but so it's an odd number, so it's not divisible by 2. How do I know it's not divisible by 3?
Well, the sum of the digits isn't a multiple of 3.
That's true, the sum of the digits is a multiple of 3.
And it's one more than a multiple of 3.
Right, this is a multiple of 3, right?
Yeah.
Yeah, so it's 1 more than a multiple of 3. Now, and so I get a number, and this number now isn't divisible by any of my primes. So either this is prime or divisible by a new prime number that we haven't found yet. But either way, it's a contradiction. There must be more primes than 2 and 3.
Yeah.
Now let's do another example. 2, 3, and 5. Let's say these are the only primes. Then I'm going to take 2 times 3 times 5 plus 1, and I get, you know what 2 times 3 times 5 is?
It's 31.
Plus 1 is 31. Okay, is this 31 divisible by 2?
No,
it's
Why not?
because it's odd.
Is it divisible by 3?
no, because 30 is.
Okay, is it divisible by 5?
No, because then doesn't
30
mean
is.
5 or 0.
Right, so I've got a multiple of 2, 3, and 5 here, and I just added 1 to it. Okay, so either this number is prime,
Or it's divisible by a new prime.
it's divisible by a new prime. Now, these two have turned out to be prime, but if you do 2, 3, 5, 7, 11, and 13, you get a number, and I had to write this one down, you get a number that's 30,031, I think, which is 59 times 509. So if I take 2 times 3 times 5 times 7 times 11 times 13 plus 1, I get this number, which is 59 times 509. So this number is not prime.
But what happens if we add...
This is the product plus 1. Okay, because you see the product's going to end in a 0 because it's got a 2 and a 5, which makes 10. I added 1 to it, and I get a new prime, 59 and 509. So Euclid said we could do this in general. If we had finitely many primes and they ended at some point, we take the product, P1 times P2 times ... times Pn, multiply them all together and add 1. This new number is not divisible by any of these primes because this is divisible by the primes and we added 1 to it. So either this number is
prime itself,
or it's divisible by some other prime that we didn't know about before.
Ooh.
So therefore the assumption that there were finitely many primes and we listed them all was wrong. So there must be no way to list all the prime numbers in a finite amount of steps, which means there must be
Infinitely many primes.
infinitely many primes. Okay, now where's our eraser?
Oh, under here.
Great. Now I want to show you one other cool fact about prime numbers. Remember I've told you before that 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. The reciprocals of the squares, what would be the next one?
it would be 1 over
25.
1 over 25. This, if you go all the way out infinitely many terms, this sums up to pi squared over 6. We can do the same thing with the prime numbers. A half plus a third plus a fifth plus a seventh plus an 11th plus all, summing up all the prime numbers.
Yep. It would.
This adds up to infinity.
Ooh.
Ooh, so even though the numbers get super small,
Yeah.
it still adds up to infinity. The squares add up to pi squared over 6.
But the primes add up to infinity.
The inverse primes, even though they get super small, like, we said 59 was a prime and 509 was a prime.
Yeah, but the squares keep on getting larger and larger and larger. How come they don't add up to infinity as well?
Well, in other words, when you take the reciprocal, they get smaller and smaller and smaller.
Yeah.
Right? And just like the primes, they get smaller and smaller and smaller. This one adds up to a finite number. In fact, cool finite number.
Pi squared
That's a
over 6.
boring finite number. Pi squared over 6. Now, pi is a little bit more than 3, right?
Yeah.
Pi squared is real close to 10. So this is about 10/6 or 5/3 or 1.66.
Yeah.
And this is infinity, which is bigger.
The infinity.
Yeah. So this is pretty amazing, isn't it?
Yeah.
Yes.
Yeah. This is one of the really neat things you learn about later on in math. And one of the books I had in college actually said this statement shows that the primes make up a big chunk of the integers because they add up to infinity. And correspondingly, that would mean the squares, most numbers are not perfect squares. Most numbers are not prime numbers either, but there's a lot of primes.
Yep.
All right.
Good job, guys. Good job. That's our talk about prime numbers.